Hello everyone, welcome to GATE Pass. I am Dr. Poonam, and in this video we are going to solve problems from GATE 2020. So the first problem which I have taken is question number 43. It gives that the pure gas, it obeys this relation PV by RT equal to 1 plus BP by RT. You can figure this out, that this is the virial equation which has been truncated to the second term. B is your second virial coefficient, and it is given that B is independent of temperature and pressure. Usually you know that B is a function of temperature. Okay. Now this PV by RT, we know from the last video that is equal to your compressibility factor Z. So I have written it. Now it has been given that your residual Gibbs free energy that is given by this integral, and this integral has to be evaluated at constant temperature. Okay. Further, the value of numerical value of B is given, and you have been asked to calculate your residual molar enthalpy in joules per mole at given pressure and temperature. So let's start this problem. So the starting point of this problem is the equation which we often see. Okay, so we have to write it like, say, GR by RT, that is given. Let me take a differential of this. Okay, so first I am going to differentiate by keeping RT constant, and I will write dg. Okay, next I will keep my G constant and I will differentiate T. So I get, okay, so 1 upon T, it will be minus 1 upon T square dt. Okay, so this is my starting equation. Now I know that I can write dg as VdP minus SDT. Okay, and H I can write as, G I can write as H minus Ts. So I am going to plug in these equations. So then my dg by RT, that is equal to 1 upon RT, I can take constant outside. Okay, so then dg is equal to VdP minus SDT, and G is H minus Ts upon, let me see, RT I have taken constant out, so T will remain dt. Okay, so you have followed up to this point. Fine. Now let's open this bracket and see what we get. So VdP minus SDT minus H upon T dt plus okay, T gets cancelled and you are left with SDT. Now this SDT and this SDT gets cancelled and you are left with V by RT, and this is dP. Okay, V by RT dP minus H by, so RT square dt, that is equal to d G by RT. Okay. Now they have asked you to calculate your HR. What is your HR? That is your residual molar enthalpy. So if I am writing this for species, I can write this for ideal gas as well. And then if I write it for ideal gas and subtract that ideal gas equation from this equation, then I can write this equation as well in terms of your residual properties. So I am going to write it like this. Okay, so now if I take a partial differential of this quantity with respect to T while keeping P constant, then I will get the value of minus HR by RT square. Okay, so that will be the equation which we will be using. So all other equations I will just erase and write that equation. Okay, let's just keep this equation for some time before we, okay, write this equation. So GR by RT, taking a partial derivative with respect to T, okay, this was R, that is equal to minus HR upon RT square. Okay, so this is the equation which we are going to use. So before we differentiate this quantity with respect to T, first of all we will have to find out what is the value of GR by RT. Now GR by RT you will have to first calculate by integrating this at constant temperature. So let's do that first. Okay, so I am using this equation and integrating over here. So what I get is gr by rt, that is equal to integral 0 to p. Now z minus 1, that is equal to, if I take 1 over here, then z minus 1 is equal to bp by rt. Okay, so that's what I am going to write over here, bp by rt, and it has to be integrated with respect to p, and there is one more p over here. Okay, now p and p gets cancelled. This has to be evaluated at constant temperature, so I can pull out t. Okay, so the integral which is left is 0 to p dp, which will be, if I apply limits after integration, it will be p minus 0. So your integral now becomes bp by rt. Okay, so you have your gr by rt, that is equal to bp by rt. Okay, now go ahead and take a differential of this, because now I am going to use this equation. So now your gr by rt is equal to bp by rt. Okay, so now let's take a differential of this with respect to t and then equate it to minus hr by rt square. So what I am going to do is, let's do this, rt upon okay, dou t, that is equal to dou by dou t of bp by rt, and that should be equal to minus hr upon rt square. Okay, now let's take a differential. P is constant over here, we have to just differentiate with respect to t. Okay, and 1 upon t, you will get minus 1 upon t square, that is equal to minus hr upon rt square. Okay, rt square in denominator will get cancelled, even minus minus sign will get cancelled. So what you are left with is hr, that is equal to nothing but b into p. Okay, now you will see that it's such a simple question. hr is equal to b into p. What is b? 10 raised to minus 4. And what is p? 1000 kilopascal. So multiply it with one more 1000, so it will be 10 raised to 6. So what you have is, the answer is 100. Okay, so this is 100 joules per mole. So mathematically it's very simple, but you should know how you arrive to this value. Okay, so just to recap, what you do is gr by rt, first you integrate by putting the value of z minus 1 from this, you calculate your gr by rt, then you differentiate this gr by rt with respect to t in order to get your hr. Okay, and then you just put the values, numerical values, and you obtain the equation. Okay, so the second question which I am going to take is question number 18 of GATE 2020, in which there were 3 relations which were given, and you were asked that which one is correct. Okay, so since in my previous videos we have already seen what is GE by RT, how it is related to your activity coefficient gamma, so I will suggest you to go back and see videos of GATE 2022 thermodynamics. Okay, but just to recap, your gamma, that is your activity coefficient, it is given as Fi cap upon Xi Fi. Okay, where your Fi cap is the fugacity in the solution, fugacity of species I in the solution, and Fi is your fugacity of species I in its pure state at same temperature and pressure as that of your solution. Okay, so this is how it is defined. Now we have already seen this equation. Now let's first use this equation. So if x1 tends to, so now let's say that it's a binary solution. So I have 2 components. So if my x1 is equal to 1, then my x2 should be equal to 0. Okay, now they have asked you that limit x1 tends to 1. So if this is x1, I just write it for, let's say, f1. x1, f1. If x1 tends to 1, what happens is that your fugacity of species I in the solution, it approaches that of the pure species fugacity. Okay, so your Fi cap in the limiting case, it becomes equal to Fi. So what happens is that your gamma 1, then limit your x1 tends to 1 is equal to 1. Okay, Now what over here, what is given is, the values are given as 0 or 0.5. So both of these are wrong. Okay. Now let's quickly see then what is GE by RT. Fine. So GE by RT, we all know that ln gamma is a partial molar function with respect to your GE by RT. Okay. So after applying my summability rule and all, I can write for the solution that my GE by RT for a binary mixture is x1 ln gamma 1 plus x2 ln gamma 2. Okay. Let's just separate this. Okay. Now you have to find out limit when x1 tends to 1. Okay, when x1 tends to 1, just now we had seen that your gamma 1 tends to 1. Okay, so when your x1 tends to 1, your gamma 1 tends to 1 and ln of 1 is nothing but 0. Okay, now when your x1 tends to 1, your x2 tends to 0 and whatever is ln gamma 2. Okay, so essentially what happens is that then this quantity becomes equal to 0 when your x1 tends to 1. Okay, so 2 is wrong and option 1 is right. So these are very simple, just requires two relations which we have already seen. Okay, so quickly you can solve it. So next we are going to solve question number 4. It's a very simple question, appeared for 1 mark in GATE 2020. Okay, so here it has been given like you have two reversible carnot engines. First carnot engine is operating between T1 and T2 and its efficiency is 0.4, and the second carnot engine, it is operating between the two reservoirs T2 and T3 and its efficiency is 0.35. Okay, so it's very simple. You have to find out T3. Okay, so how do you do it? Now let's write down what is efficiency. So as usual I will start with the basic. So let's say if I have a carnot engine which is operating between two reservoirs, one is at TH, the other is at TC. It draws in QH amount of heat, does W amount of work and rejects QC amount of heat. Okay, then your efficiency is given as output, which is W, upon what has been input to this, that is QH. Okay, so your desired output is the work which is generated. Now what is work over here, how much is done? That will be equal to QH minus QC. Okay, so I can write QH minus QC upon QH. So then it becomes 1 minus QC by QH. Okay, now your efficiency is given in terms of your heats which are rejected and extracted from the two reservoirs respectively is this. Okay, now you all know that a Carnot engine, Carnot cycle on PV diagram, how you can draw it is two isothermals which are connected by two adiabatics, and all of these four are reversible processes. Okay, so two reversible isotherms with two reversible adiabatics. Okay, now this is at higher temperature, let's say this is at TH, this one, so it takes in QH, absorbs QH amount of heat, and this isotherm, it is at TC and it rejects QC amount of heat. Okay, now let's assume that this is an ideal gas which is the working fluid. Then you can derive using the equations which you have for ideal gas. For an isothermal process, for an adiabatic process, you have all those equations. You can easily derive that your QH by QC, that is equal to your TH by TC. Okay, it's given in your Smith-Wenders and you can go and check over there. So for an ideal gas you can derive this, and from Carnot theorem we know that the efficiency of any reversible engine which operates between the two reservoirs which are at the same temperature, okay, at any given temperature, then their efficiency is same. So your efficiency does not depend upon the working fluid. That is your one of the Carnot theorems. Okay, so in this case, even though we have derived this relation for ideal gas, it holds true for all other working fluids. Okay, so I am just going to write that is equal to minus TC by TH. Now your question is very simple. First of all, what I am going to do is, so this was all a background, erase it. Now let's apply this to your first engine. So N1 is equal to eta 1, that is equal to 0.4, that is equal to 1 minus T2 I don't know, T1 I know. So from that I calculate my T2. Okay, so do that and you will find that your T2 comes out to be 480 Kelvin. Now let's apply this equation again for the second engine. So your efficiency is 0.35, that is equal to 1 minus 480 upon, no, I am writing it wrong. It should be 1 minus T3 upon T2. T2 we have calculated as 480. So solve this and you will get your T3 as 312 Kelvin, which is the answer. Okay, so very simple question. For 1 point you can quickly do it. It just requires this. Okay, so I hope you enjoyed my video and understood the problems. If you have any questions, please leave them in the comment section and I will get back to you. And if you liked the video, please don't forget to subscribe to my channel and also click the like button. Thank you so much for watching.